We just learned that in saturation, the current ID and the voltage VDS are independent. A small change in VDS, denoted by delta VDS, will result in no change in the current. Therefore, the incremental resistance given by delta VDS over delta ID will be infinite. This is the incremental resistance looking into the drain of the NMOS. However, this is based upon the assumption that once the channel is pinched off, that is, it is at this stage, then further increase in VDS does not affect the channel's shape. In reality, increasing VDS beyond VDS sat, that is the point where the channel is pinched off, does affect the channel. The channel's pinch-off point, this one here, moves away from the drain and towards the source. Like this. The voltage across the channel remains constant at VDS sat. The additional voltage appears across the depletion region between the boundary of drain, here, and the end of the channel, here. This voltage helps the electrons cross the depletion region into the drain. Notice in the figure that the channel length is also reduced. This is channel length modulation, and it must be taken into account in calculations when necessary. Remember that ID is inversely proportional to channel length. Look at this formula. So, with the decrease in channel length, ID increases with VDS. Accounting for the channel length modulation, the equation can be rewritten as on your screen. We can further rewrite this. Now let's introduce another parameter. And so we can again rewrite this equation as this one. Introducing another parameter, we can further change our equation to be this is the complete equation which accounts for channel length modulation. Now let us see graphically how channel length modulation modifies our ID-VDS characteristic. You can now see that the graphs in the saturation region have a gradient as opposed to the horizontal lines that they were before. When they are extrapolated, they intercept the VDS axis at the point VDS equals minus VA, this one. Putting this voltage minus VA into this equation, where ID equals 0, gives us VA equals 1 over lambda. This voltage VA is usually referred to as the early voltage, named after J.M. Early, who discovered a similar phenomenon for the BJT. So we have now discovered that when channel length modulation is taken into account, the saturation values of ID do depend on VDS. Therefore, the resistance in the saturation region is no longer infinite. We can calculate an expression for it. This one on your bottom right. This can be rewritten as VA over ID, where ID is the drain current without the channel length modulation taken into account. Whenever we solve problems, we will make it explicitly clear whether we want to take channel length modulation into account or not.